Okay, we're going to hopefully finish this chapter. If not, we'll finish it next time. But we are going back to 21, which was nuclear chemistry. And last time we talked about several things. I think we talked about balancing nuclear equations, which once again, not too difficult. Basically, two things you need to make sure of. You got your mass number on the left equals your mass number on the right when you add them all together, and your atomic number on the left equals our atomic number on the right. Again, it is that atomic number that's probably going to allow you to figure out maybe what element is missing. If something goes through some type of radioactive decay by giving off a certain type of particle or emitting a particle, that particle ends up on the product side. While if somebody's doing an electron capture or some type of bombarding, those particles end up on the reactant side. We also talked about stability and a couple of different ways to look at stability. One main way is the basically neutron to proton ratio. And depending on whether or not your neutron to proton ratio is sort of high or low, there is sort of what is referred to as the belt of stability or valley of stability. And if you find yourself with your neutron to proton ratio too high or too low, what will happen is these guys will go through again a decay process to try to move them into a better direction towards that valley of stability or belt of stability. They may not get there with the initial sort of decay process, but they should kind of move themselves to a proper sort of location. For too high, it's going to probably go through a beta decay to do that. If it is too low, it will do either a positron emission or an electron capture. And again, that will move everybody up to the sort of the right situation or towards the right situation. We also talked about the most stability sort of occurs when you have even protons and even neutrons. That is where you have the most stable sort of isotopes that are developed. The worst in terms of stability is odd and odd. So an odd number of protons, odd number of neutrons are also sort of a really bad sort of combination. So if you're looking at a nuclei that has odd for both of those guys, pretty good chance it's probably going to be unstable. Or if you have the even for both of those, probably a good chance that it will be a stable guy in that situation. We also talked about a decay series, and that is a series of really decay events that occur until something that is relatively stable sort of develops. You could do that by simply writing each sort of equation, and whatever you make of the first equation is the next thing that goes through sort of the decay process. And you could just again do sort of like the balancing equations type, nuclear equation type of process. If it involves just an alpha or beta decay that occurs and you're maybe just interested in what you get at the end, you could do a more mathematical approach. For every alpha decay, you're going to take 4 away from the mass number and 2 away from the atomic number. And for every beta decay, you will add 1 to the atomic number. So that's sort of a quick way, if you're again just sort of interested in what you get at the very end, that you can kind of go through it and figure it out. I think we finished up talking about radioactive decay. And radioactive decay, it does follow first order kinetics. And really, although in nuclear chemistry, they sometimes use some different symbols, it really is the same sort of kinetics that we talked about at the very beginning of the semester, where we have our 2 main equations. Our natural log of A is equal to our natural log of A naught minus KT, where our half-life is equal to the natural log of 2 divided by K. K is sometimes referred to as the decay constant when you're doing nuclear chemistry. It's the same idea as the rate constant in sort of chemical kinetics. Also, the other main difference is sort of what we use in our A's here. So before in kinetics, we usually use, again, concentration or molarity, but very common here in sort of nuclear chemistry, we use units like grams or milligrams. We also could use rates of radioactive decay. So you can put the rates in there as well. So it doesn't necessarily be concentration. As long as A on both sides there is the same unit, then you'll be okay. We also will sometimes see them again use N for nuclide for these guys. So sometimes they'll use N instead of A in nuclear chemistry. Sometimes they'll also use lambda for the decay constant. So sometimes they'll use the lambda symbol for that as well. And again, sometimes they'll use N for this guy here instead. Any questions on any of that stuff there we talked about there? All right, so I think we did an example. I think we did this one, I believe. All right, so we also could look at sort of kinetics and radioactivity and use it to help us perhaps date how old something is. We could do carbon-14 dating, where carbon-14 has basically a half-life of 5730 years. It will decompose into nitrogen-14, give off a beta particle. Also, uranium-238 dating can be used, and sometimes you figure out how much lead is left and subtract it from how much you started with, and you can figure out how much you get there. But these are two common ways. We would still, again, here use our first order kinetics to solve these problems. The difference is usually in these type of problems, time is oftentimes what we're looking at. So when we solve for time, obviously that would be what is left over. Again, our initial here and our final and our decay constant. The other thing that we talked about is a lot of times you will need to use both of these equations together. A lot of times you're not given the decay constant, but you are given the half-life. So you have to use the half-life equation to get the decay constant, and then you can use the top equation there. So why don't you try one here? An ancient skull gives 4.5, and that is a unit of radioactive decay. That is disintegrations per minute. And this is actually per gram of carbon, not Celsius. So that's per gram of carbon. If a living organism gives 15.3 disintegrations per minute per gram of carbon, how old is the skull? So because it's per grams of carbon, we're going to assume carbon-14 dating here. So we would use the carbon-14 half-life, which is 5730. So why don't you give it a try and see what you come up with? We are looking for how old it is, I believe. So anything involving radioactive decay, always going to be first order kinetics. So you can really just lay up your equations here. In this particular case, we have an ancient skull that gives 4.5 disintegration per minute, a living one, 15.3. Living would be our initial, and our kind of ancient one, our dead thing there, would be our final. We are looking for how old it is, which is time. So very common in these type of problems, we are missing the decay constant to do that. That is why we do have our half-life given to us. So we do want to find the decay constant so that we'll have the last thing that's missing there. So in this case, we will rearrange, and we see the decay constant is the natural log of 2 divided by the half-life. That gives me my natural log of 2 divided by 5730 years. And that gets me, we'll call it 1.21 times 10 to the 1, 2, 3 minus 4 reciprocal years. So once again, this is first order. So rate constant, decay constant should have units of 1 over time, basically, which is what we see here, like 1 over seconds, 1 over years. We now have really everything that we need to solve for this. We'll go in with our natural log of 4.5 is equal to our natural log of our living there, which is 15.3, minus our 1.21 times 10 to the minus 4 reciprocal years times t. So remember, t here is time. I'm going to take the natural log of 4.5, and then I'm going to subtract the natural log of 15.3. And if I do that, I end up with minus 1.223775 equals minus 1.21 times 10 to the minus 4 reciprocal years times time. We're going to bring this to the other side. When we do so, we also get the years to flip to the top. And by doing that there, we end up with a time that would be in years, 10114 years, or maybe like 1.01 times 10 to the 4 years, about 10,000 years old. Yeah, seems pretty old. Any questions on any of those steps there? So once again, obviously very similar, not really very similar. It is the same thing as what we did in kinetics in that first chapter there. Yeah. Any questions on that one there? All right, so let's try another one here and see what you come up with. So we find a grain of rice there. There you go. Archaeologists dated civilization to 15,600 years old. If a living sample gives 20 counts per minute per gram of carbon, what would be the number of counts per minute per gram of carbon in a rice grain that's found on the site? So once again, we're dealing with carbon. So we'll use the same half-life as we had on the previous problem, 5730 years. All right, give it a go, see what you come up with. So once again, we're going to roll with our first order equations here. And in this particular case, we are looking for how many counts per minute that would be found. So that is the old one. A living one would be our initial. We have the time, which is 15,600 years. So once again, here we are missing the decay constant. So we will use our half-life to get us there. And again, it would be this. We'll come out the exact same as what we just used in the previous problem, since we're still doing carbon. So we'll end up with the same value. And now we have obviously what we need there. In this case, we would then end up with the natural log of A is equal to the natural log of our initial, which is 20 counts per minute, minus our 1.21 times 10 to the minus 4 reciprocal years times our 15,600 years. One thing, as we talked about last time, is you do want to make sure you're careful on units here. They're both in years, so everything's going to cancel out. But again, sometimes they are not the same unit, so you want to watch that. We're going to clean up the right-hand side there. We're taking the natural log of 20. We're then going to subtract it by 1.21 to the minus 4 times the 15,600. Gets us a natural log of A is equal to 1.10813. We're going to E both sides there. And that would give us that our final counts per minute would end up being 303. The units here would be the same thing as the previous one, the counts per minute per gram of carbon, basically. Any questions on that one? It does make sense. This is a unit of radioactive decay, which means the older piece of rice should not be given off as much radioactivity as it's decayed over time. So the counts per minute here should be less than obviously a fresh one right off there to start with. Any questions on first order kinetics or radioactive decay? So again, good news is it is pretty much the same calculation as what we did earlier. Okay, so the next thing we're going to talk about then is we're going to talk a little bit about fission and some of the energy that comes out during the fission process. So last time we talked about fission, and fission really can be done one of two ways. It can be a spontaneous fission where we have an unstable nucleus that really will split off into two new nucleuses. It will give off some neutrons and some energy. You could also make it happen by basically bombarding a stable nucleus with something like a neutron. It will become unstable, and we'll start to go through this. During the process, though, of fission, there is some mass of the nucleus that's converted into energy. So there's a slight difference in the mass of basically the protons and the neutrons that make up the nucleus and the mass of the actual isotope itself. And that slight mass difference is what is known as the mass defect. So the mass defect is really kind of the difference in the mass of the individual protons and neutrons to make up the nucleus and the mass of the entire sort of isotope. You could actually calculate the energy associated with that by using Einstein's equation here, which is E is equal to mc squared, c being the speed of light, which is 3 times 10 to the 8 meters per second. M here is the mass defect in this application. And sometimes the mass defect is like the little delta symbols used for it as well. We've talked a little bit about it earlier in this chapter that there is a very big difference in the amount of energy that is produced in a fission process versus sort of an exothermic reaction. So as you can see it here, exothermic reaction 10 to the 6 joules, 10 to the 13 joules of energy just through going through this fission sort of route. So there's a lot more energy that is sort of given off. So when we talk about mass defect, and sometimes what is referred to as binding energy or nuclear binding energy, when a nucleus forms, some of that mass, again, from the separate nucleons, and the nucleons, again, are protons and neutrons, is converted into energy, and that difference is what is referred to as the mass defect. So there are a couple of conversions down here that can be used in place of E equals mc squared. You can actually do it both ways. 1 mega electron volt is 1.602 times 10 to the minus 13 joules, and 1 AMU of mass defect is 931 mega electron volts. Binding energy, and more specifically binding energy per nucleon, is another measure of stability. So the greater the binding energy per nucleon, the more stable the nucleus is. So you could use binding energy per nucleon to help you determine stability. So let's just say we look at an example here, and we have this isotope of fluorine that has a mass of 18.9984 AMU. And we wanted to calculate the nuclear binding energy per nucleon. So we could do this by first off figuring out the number of protons, which should be 9 in this case, equal to the atomic number. The number of neutrons is 19 minus 9, which would be 10. Will give us our number of neutrons. So to calculate the mass defect, what we would do is simply take the number of protons and we would multiply it by the atomic mass of a proton, which is 1.007825 AMU. So that's the AMU for a proton, basically. We would then add it to 10 times the atomic mass for a neutron, which is 1.008665 AMU. And again, these are our neutrons. We would then subtract it from the atomic mass of the isotope, which is 18.9984 AMU. And if we do that there, we will end up with 0.1587 AMU. This is what is known as the mass defect here. That is the amount of mass that's going to be really converted into energy through this process here that's going to occur. To calculate the actual binding energy, again, there's two ways you could do it. So we'll take a look at both here. The first way would be to do Einstein's equation, which is E is equal to mc squared, where once again, the M is our mass defect. So this would be 0.1587 AMU. This would be 3 times 10 to the 8 meters per second squared. And this will give me bless you. punch the numbers in there, right? 1.43 times 10 to the 16. The units here are AMU, meters squared, seconds squared. We're typically looking for joules. So one conversion you might remember is a joule is a meter squared, seconds squared. I'm gonna get that right there. Try that again. Take two. It is a kilogram times meters squared over seconds squared. There we go. So we're close there, but we have an AMU. So we could actually use a conversion here to get us to joules, which would be 6.022 times 10 to the 26 AMU per kilogram. Those guys are going to cancel, and that would get us 2.4 times 10 to the minus 11 kilograms meter squared second squared, which is a joule. This is Avogadro's number. Yes, Avogadro's number is to the 23rd, right? Which is a gram. To the 26 makes it a kilogram. So that's why it's to the 26 in this case and not 23rd. Typically speaking, we oftentimes will want to know the binding energy per nucleon. Nucleons, protons, and neutrons. So we would take this number and divide it basically by the mass number here, which is 19 nucleons. And that would get us divided by 19. That is not that. 2.4 minus 11. Yeah, 2.4 minus 11. There we go. Divided by 19. Gets us a 1.3, we'll call it, times 10 to the minus 12 joules per nucleon. First off, any questions on that there? So this is one way you could do it. And this is a common unit of binding energy, which is joules per nucleon. Another common unit of binding energy is mega electron volts per nucleon, where you could use that conversion there that we saw on the previous page, where 1.602 times 10 to the minus 13 joules is 1 mega electron volt. So you could divide it basically by that number. Gets you approximately 7.884 mega electron volts per nucleon. That is another very common unit, which is mega electron volts per nucleon as well. Now, if you don't want to use Einstein's number, you can use these two conversions here just right off the bat. They're really based off Einstein's equation, and it could get you to the answer you're looking for. So if you did that, you could just really pick it up right here with this number and take 0.1587 AMU. You could do your AMU is 931.5 mega electron volts. And again, if you do that, you will get 0.1587 times 931.5. Gets you like a 147.8 mega electron volts, which if we then divided it by 19 nucleon, gets us our approximately 7.8 mega electron volts per nucleon. Again, with rounding, might be a little bit off. And then you also could obviously use the mega electron volt to joules to get yourself to joules as well. So you can go that way and get it, or you could go the other way and get it. It is really a personal preference. They're both basically based off of the Einstein equation there. Any questions on doing it that way there? All right, so why don't you try one here and see what you end up with here. Actually, we'll take a look at this graph here first. This is a graph of binding energy per nucleon. And we actually see the highest in terms of stability actually is iron 56 there. Again, it's a measure of stability, and we see it on this graph as well. Most stable nuclei are in that region. And obviously, if you go one way or the other, you're going to end up with more of an unstable sort of situation that's going to occur. So why don't you give this a go, calculate the mass defect and nuclear binding energy. Let's do both, joules per nucleon and mega electron volts per nucleon. And again, a proton is 1.007825. Neutron 1.008605. All right, give those a go, see what you come up with. Let's take a look. So we're dealing with carbon 16. So that means we go to periodic table, we see carbon's number 6 there. That's important because that tells us we have 6 protons. 16 minus 6 would tell us we have 10 neutrons in this case. So we'll start with our mass defect here. And that would be our 6 protons times 1.007825 AMU, which is our mass of our proton. We then will add it to 10 times our neutron's mass, 1.008665. We then will subtract it from the atomic mass of the isotope, which was given to us of 16.014701 AMU. That's going to give us looks like a mass defect of 0.1189 AMU. Any questions on that part there? At this point, it's a couple of routes you take. Do Einstein's equation, or since they do want mega electron volts per nucleon, we might as well just maybe just use the conversion there. Be a nice way to do it. 0.1189 AMU, again, using that in AMU will give us 931.5 mega electron volts. Taking that times 931.5. Going to give us, we'll call it 110.8 mega electron volts. Since we do want it per nucleon, we could actually stop right here and kind of do a little division to get that first answer, which would be really the mass number, which is 16 nucleons, which is our protons and our neutrons, yielding us about a 6.922 mega electron volts per nucleon here. We also want it in joules per nucleon, so we could also just use the conversion factor to do that little conversion at this point, since we already have it per nucleon. We could use our 1 mega electron volt is 1.602 times 10 to the minus 13 joules. Those guys will cancel, and that would get us 1.1 times 10 to the minus 12 joules per nucleon in this particular case. Any questions on that there? Again, you could have put equals mc squared divided by that Avogadro's number to the 26th, and that would have got you to the joules part first. And then you could obviously go the opposite way there as well. Any questions on any of that there? All right, let's try one more here. Wrap it up, I think. Let's do the binding energy per nucleon. We'll do mega electron volts per nucleon here for iron 56. And once again, the proton is 1.007825. And the neutron 1.008665. All right, see what you come up with here. All right, so iron 56 obviously being the mass number, go to the periodic table, get the atomic number, which is 26. That means we got 26 protons in this case, and 56 minus 26 gives us 30 neutrons in this case. So once again, starting with the mass defect here, we're going to take our 26 times our proton's mass. We're going to add it to 30 times our neutron's mass there. And once again, we're going to subtract it from the isotope's mass, which was given to us, 55.93494 AMU. That is going to get us 0.5285 AMU. Again, in this case, if you wanted to do the Einstein equation, you would take that and times it by 3 times 10 to the 8 meters per second squared. And gets you 4.76 times 10 to the 16 AMU meters squared second squared, converting it into joules here, dividing by our basically Avogadro's number. Getting us 7.9 times 10 to the minus 11 joules, which in this case, since we wanted mega electron volts, if we chose to go this way, we might just want to convert it now into that, which would be 1.602 times 10 to the minus 13 joules per mega electron volt, divided by 1.602 minus 13. Gets us about 493 mega electron volts divided by our mass number, which is 56. Gets us about a 8.804 mega electron volts per nucleon. Again, if you round it a little bit or went the other way, might be slightly off or slightly different than that. Question on that conversion there. So we again could use our nuclear binding energy per nucleon as a measure of stability. So if we look at the 3 that we just calculated here, our iron 56 was 8 basically mega electron volts per nucleon, or 8.8. Our carbon 16 here was 6.9, which is less, and our original fluorine that we did back here was about 7. So in terms of stability, iron 56, as we saw, which was on top of that chart right there, is the most stable out of those 3. Would be followed by the fluorine, which was 7.7, and then followed by the carbon 16, which was about 6 and change, or whatever we had there. Any questions on how to calculate nuclear binding energy? Okay. So to kind of finish up talking about here, nuclear chemistry, nuclear transmutation is the process at which we sort of shoot particles, if you will, at isotopes, and obviously sometimes it makes them very unhappy. So we could use a particle accelerator here, magnetic field, electrical field, kind of getting the particle spinning really, really quick and then into our target. So here, if we shoot curve alpha particle at these guys, we end up with some new elements that are formed, and this is what is sometimes referred to as transmutation. This is also the way that you can basically start a fission reaction, is by doing this process. These are the transuranium elements, and they're all kind of, as you go through here, as a result of some type of particle being shot at it. It's where we get all of our sort of nice names like americium, berkelium, californium, all these sort of man-made isotopes, if you will, that typically are in the bottom there of the periodic table. Comes through this process of basically shooting particles of other isotopes. Doesn't make them so happy. And that is what we see here in this process here of nuclear fission. This is sort of transmutation here where we're sort of doing that process, shooting a neutron at a uranium-235 element. It becomes unstable on a bowling pin here, and then it will go through the fission process at that point. We'll split off into these two new nucleuses, in this case, strontium and xenon. The result of that is we actually make a bunch of more neutrons in this process, and a lot of energy is usually associated with this sort of reaction. And again, by comparison, you get like 10 to the 13 joules in this type of fission reaction versus that if you took like a ton of coal and did a combustion reaction, you get about 10 to the 7 joules of energy. The reason the comparison is there is the traditional power plant, right, is usually historically been powered by burning coal. A nuclear power plant, for example, is done through a fission reaction is used. Now, you don't always necessarily get these same two sort of new elements that are formed here. These are sort of peaks of mass numbers that sort of commonly form, but you're not always guaranteed the same two guys will always come out if you shoot a neutron at 235 uranium in that particular case. So let's talk a little bit about the nuclear fission reaction a little bit more. What can happen in this particular case is we could get a nuclear chain reaction, which is basically a self-sustaining sequence of these fission reactions that occur. And the reason for that is very simple. Basically, to kind of kick off the reaction, you need a neutron. When this fission reaction takes place, you make a bunch of neutrons, which then could obviously go back around and kind of keep the process going and going. To minimize that, we usually like to treat the material below what is necessary to sort of keep this reaction going and going forever. And that is what is known as the critical mass. So the critical mass is basically the minimum amount of material you need to, if you kick off this reaction, it will continue to kick off. So in a non-critical sort of situation, you could kind of keep it under control. It eventually will not be able to sustain it forever. In a critical sort of reaction, you get this exponential growth that occurs, again, because part of the products is what you need basically to start it. So it kind of grows exponentially in a situation. Also why a nuclear sort of bomb, sort of like this, you have a subcritical mass on each side. When the bomb hits, the triangle goes in, creating a critical mass of fissionable material, which obviously can continue this process. This process is really bad because every time it does it, you create a bunch of radioactive products. Yes, that gives off radioactivity, gives off maybe beta particles, alpha particles, gamma particles, and that's obviously not good to be around. This fission reaction is actually the same reaction that, or a similar reaction that is used in a nuclear power plant. For us, San Onofre, I think, is the closest. I don't think they're actually functioning anymore, but that is, I think, our closest nuclear power plant around here. They usually are around a really big body of water like the ocean, or if you're inland like in Arizona, they have really big cooling towers of water usually near them and stuff like that. So in a nuclear reaction, or just in a power plant in general, regardless of the type of power plant, they all basically kind of work the same way. You basically have like water and you heat the water. And when you heat the water, you create steam, right? And steam goes out to the turbines, to the generators, and you get light, right? Nice thing about steam is you could also cool it back down, right? And sort of recycle it in a nice process, which is why they are typically around big bodies of water, especially nuclear power plants, to do that. So the difference is between a traditional power plant and sort of a nuclear power plant is how they heat the water. In a traditional power plant, historically, they heat the water by heating coal, and the coal obviously gives off a lot of energy and heat, heats the water, creates the steam. In a nuclear power plant, they do a fission reaction where inside sort of the nuclear part of the reactor there, they have what are referred to as fuel rods. And these fuel rods are like little pellets, like eraser size pellets of uranium, basically, that basically will start that reaction. As the reaction goes, they have sort of piping through here that has the insulated radioactive sort of water, if you will. And that's going to heat the bigger source of water, which will create the steam out to the turbines. Again, using that big body of water to cool down the water or the steam to sort of recycle it through. So why does it not go out of control? There's several sort of control factors that are in a nuclear power plant. One is a control rod. Control rod is guys that have something like cadmium on it, which is a neutron absorber. Why would absorbing neutrons be good in this type of reaction? Because in this fission reaction, it is the neutron that kicks it off, right? And you make neutrons. So if you take out some neutrons from that process, it will keep the reaction not going exponentially growing because you're taking out a lot of the starting material. In addition, they use usually not a critical mass. So they keep the critical mass obviously below what is necessary to do so. Usually they're very big concrete sort of containers like you see out there in San Onofre to contain all that inside there. Try to keep sort of the radioactive part away from obviously the other part. Obviously, regardless of the sort of type of power plant, there's positives and negatives. Burning coal obviously creates a lot of pollutants in the air. Obviously, to get to the coal, you might have to strip out some land and stuff to do that. Obviously, a fission reaction creates a lot of radioactive byproducts as a result of it that are around a very, very long time. And it is like, what do you do with all that stuff? Who watches it? Who controls it? For a lot of years, nobody wanted it coming through their town. So for a lot of years, nuclear power plants would just store everything on site. Years ago, they started digging a big hole in the Nevada desert there. And I think they've started using it now where they will ship all that kind of stuff to be watched over the years. This is also why, you know, some of the byproducts of nuclear fission is really important. It's sometimes referred to as spent fuel. And for example, you know, if you look at any of these sort of half-lives here, how long you got to keep them in storage, it's thousands and thousands of years until they're no longer super hazardous, if you will. So that's a long period of time to sort of keep an eye on that. Any questions on that there? Now, nuclear fusion is a little bit different than fission. In fusion, what we're doing is we're taking two smaller nucleuses and putting them together at extremely, extremely hot temperatures, like we're on the sun and vacationing over here, and that high of temperatures. And it does release a lot of energy, which again, in a lot of those movies, they want the guy that made cold fusion. So you didn't have to do it at those high temperatures, but it does, as we see here, a couple hydrogens coming together to make a larger guy. It happens at really, really large temperatures. We also sometimes will use, obviously, radioactive isotopes in medicine. As we might have touched upon before, you obviously would want a small half-life if you're using something in a medical purpose. Otherwise, again, your follow-up appointment will be a lot of years down the road. So here's just some examples of things that can be used or have been used. Sodium-24, you can follow blood flow, iodine-131, your thyroid, technetium-99, imaging. The nice thing about isotopes that are radioactive and regular sort of elements that are non-radioactive is that pretty much they behave the same in your body. So you basically can get some type of radioactive sort of guy in there as a tracer. You could follow the radioactivity. It will sort of highlight everything where it's at and what's going on with it. So it's a very good way. In the laboratory, we also do that as well. We sometimes will use a radioactive version of a element. So I used to do research on copper. So we're interested in where copper was all the time. So we would use radioactive versions of copper, and you could just follow the radioactivity to sort of see where everything sort of ended up. Obviously, there's a bone scan, and again, it sort of highlights all those things here as well. When you do work with radioactivity, this is something you use a lot, which is a Geiger counter. It's like a little wand. It makes a little clicking noise, beeping sound. Hopefully it doesn't beep a lot when you point it at yourself after you've been using it. But it measures radioactivity, and you typically use something like that. You also a lot of times will wear a ring and a little badge. And usually if you work with the radioactivity a lot, they will develop those after so long. They used to be filmed and go like, you're a little too radioactive, you should take a break for a while and stuff like that. So, you know, your exposure to it is really important for safety. Using something like this to make sure you didn't contaminate the whole entire place, also really important. If I hold the Geiger counter up, will it make a sound or will it be quiet? It will make a sound. It's background radiation. Yeah, that's something you hear a lot when people use a Geiger counter. It's just background radiation. It shouldn't be beeping super loud, but it will click and stuff like that and beep because there is background radiation. But obviously, if it beeps a lot, that's probably not so good. You should also always check your shoes if you've ever worked with radioactive material, because people spill things, you walk on it, you take it home with you. Not a good idea. So you always test your shoes when you're doing those type of things. Speaking of that, you know, we do get exposed to radioactivity in a variety of sources, and there's a couple of measurements of the biological effects of radioactivity. Rad and a REM. A REM is sort of an equivalent for man. And you can see things like cosmic rays, dental x-rays or medical x-rays, air travel. You happen to live near a nuclear waste or weapons test site, perhaps you get a little bit more than that. The REM is the sort of human equivalent. And as we talked about, as we saw at the beginning, you know, depending on the type of emitter it is, you know, there's sort of a factor for it. If you remember, the alpha particles don't travel as far as the beta particles that don't travel as far as sort of the gamma rays. That's why you can see alpha particles, you can take a little bit more doses there before it gets too bad for you, as opposed to, say, a gamma ray where the factor is 1. So sort of almost a direct measurement that occurs there. Any questions on that? That's strawberries. Lovely. Any questions on any of that there? All right, that wraps up chapter 21.